Okay, so in this particular video, we will look into contact forces. Uh, the first problem here requires us to find the acceleration of these two blocks, okay, which are stacked on top of each other. The bottom block rests on a frictionless surface, whereas the surface between the top and the bottom, okay, has friction, and there are two components. There are two friction coefficients. The static friction coefficient is zero point 0.6 and the kinetic friction coefficient is zero point 0.4. Okay, so the force on the top block is 100 newtons. Okay, there is no explicit external force on the bottom block. So if we find the frictional force between the two blocks, that is nothing but mu times m1 times g. Okay, and if you look at the static friction force, it is nothing but 0 0.6 times 10 times 9.8. Okay, that roughly equals 58.8 newtons, and therefore, we can conclude that the top block actually slides on the bottom. Okay, we can conclude that. So so if we look at the equation of motion of the top block, okay, let's draw a free body diagram for that, okay, for the top block. And so here there's a force on the top block acting towards the left. Okay, that's F equals 100 newtons. There is a frictional force that's acting in the opposite direction. Okay, and this comes from kinetic friction. Okay, so so the net force on the top block on M1, okay, the net force on M1 is F minus the friction force equals M1 times A. Okay, so the acceleration equals the the externally applied force minus the friction force divided by M1, and here the force is 100 newtons minus the frictional force here is 0 0.4 because it's kinetic friction here, times 10 times 9.8 9.8 divided by 10. Okay, and that gives us 6.28 meter per second square. Okay, so this is A1, I would say. Now if you look at the acceleration, okay, of the second block, acceleration of the second block, so here uh, if you look at the free body diagram, okay, so the only force that's acting on it is the frictional force, and the frictional force tends to pull, okay, it tends to pull this bottom portion, the bottom block forward. So here the frictional force, okay, the frictional force here equals m2 times a2. Therefore a2 equals the frictional force, that is mu times mu kinetic times m1 times g divided by m2 equals 0 0.4 times 10 times 9.8 divided by 40, okay, is 0 0.98. 0.98 meter per second square. Okay, so this gives you a flavor for how to uh, uh, address situations in which the frictional force actually helps with the motion. So just to recap, the frictional force prevents this upper block from sliding forward, but the frictional force is the one that makes it possible for this bottom block to move forward. So the frictional force actually drags it forward. Okay, so that's the important part. So here we have a two block system. We have a two block system, okay, in which this mass here is being pressed against this mass. Okay, and there is a friction between these two masses. Okay, between the surface that separates these two masses, and these are being pushed along by a force. So the ask is, or the question is, what is the magnitude of the force that prevents this mass from sliding down? Okay, so that's the question. So if we understand this problem correctly, so let's try to build the free body diagrams for this. So for the mass denoted by little m, the free body diagram is such that the force acts in the right, towards the right. The contact force between the two pushes this towards the left. The friction force acts upwards and its weight acts downwards, right? If we look at the mass capital M, it's just the contact force that acts on it towards the right. Okay, so now uh, so let's write the forces, the the Newton's law for of motion for the two masses. For the, so we get F for minus F contact force equals M times A, and the contact force equals capital M times A. Okay, so both of these have the same acceleration because they move together. So if we, so here if we add the two together, we find that A equals capital F divided by little m plus capital M, right? So the contact force here equals M times A. This is nothing but M times capital F divided by little m plus capital M. Okay, so that's the contact force. So now the friction force, okay, here equals mu times the contact force, okay, equals mu times m divided by m plus m times F, and that should exceed the weight of the little block. Okay, therefore the force here should be greater than equal to little m divided by big M, okay, times m plus m times g divided by mu. So let's compute that. This is 16 divided by 88 plus 16. Sorry, this is 16 divided by 88, okay, times 88 plus 16 divided by 0.38 times 9.8. Okay, so times 9.8, and so let's compute that. So 16 divided by 88 times 104 divided by 0.38 times 9.8 equals about 488 newtons. Okay, roughly. So this gives you an idea of how to find this force. Okay, so the interesting thing here is that if you apply this force, that's greater than about 488 newtons, then the first block will not slide against the second block. See, so the important thing to understand is that the second block is free to move. Okay, there is no friction on this on the big block here when it rests against the ground. Okay, there is no friction on that, but there is friction between these two blocks. Okay, and that's what you're trying to take advantage of to prevent this block from sliding downwards. Okay, so I hope you get a flavor for how to use these contact forces and to solve real life problems. So if you like this video, please click on the like button and subscribe to this channel. Thank you.